तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last couple of lectures we talked about adders as the basic building block of arithmetic circuits which form a major unit of computers. There are other arithmetic operations. Adder is only one of the elementary operations, but there are other arithmetic operations like subtractors, subtraction, multiplication. So you can have arithmetic circuits designed for each of these operations. Also, the concept is almost the same. What did you do in the case of adders? We had to write the truth table and we had to get the corner map and get the simplified version and then implement it, and if possible try to manipulate the simplified version to a form which is more amenable for practical implementation, like exclusive OR gates. We also saw methods of speeding up, because speeding up is important. In the case of our adders, we saw there is a technique called carry look ahead. We also mentioned there are other techniques which we are not going to get into. So likewise, you can always do for subtraction and multiplication. So if you want to build a subtractor, for example, you have the half subtractor and full subtractor. If you are only going to subtract 2 bits without considering the previous bit, you have a half subtractor. And if you want to do a subtraction of a bit series of bits, then when you are considering subtraction of the previous bit, you will have to see whether one has already been borrowed from that location to the previous location. So just as a carry in the case of adders, we will have a borrow in the case of a subtractor, and similarly we will have a borrow out. So we can have, like adders, 2 inputs and a carry in and a sum and carry out as outputs. You can also have for subtractors 2 inputs and a borrow in and a difference between the 2 bits and borrow out. So you can draw similar truth tables and similar circuit implementation using corner maps. We will not get into that because we have already seen enough of this large number of these corner map techniques or truth table techniques. Doesn't matter what the function is. Once you define a truth table, once you define the corner map, implementation is straightforward. So there is no point in going on talking about different types of circuits. Of course, more number of circuits you design, you get more practice. But there is another scheme of subtraction called complement subtraction. That is because the hardware in your computer, you want to have a hardware arithmetic logic unit, which is just the arithmetics and logic functions. You like to have that as compact as possible. You don't want to have an adder unit and a subtractor unit like that. So if it is possible to combine more than one operation using a hardware unit, that is a sort of a desirable feature in hardware design. So for this purpose, we will talk of now what is known as subtraction by complement numbers. Subtraction using complement numbers. What is a complement of a number? Depends on the number system. In a decimal system, see, in any number you have a base. Decimal system, the base is 10. In binary system, the base is 2. They also call it radix. Base or radix. So, depending on the number of digits or the positions or the bits, you define the complement as the highest possible number you can represent minus the number. So let us say in the case of any general radix R R's complement of a n bit number, n digit number, or n digit is for decimal, bit for binary. So since it can be R, can be anything, I don't know whether to call it digit or bit, I can say n positions, whatever. Number is R power n minus the number. R's complement of a number n digit number n. N is the number, I think I have used a wrong variable, that's okay. One is small variable, small and the other is a capital. N is the number, n is the number of digits. What I mean by this is, if for example, let us say R is equal to 10, decimal system, and let us say n is equal to 4. There will be 4 digits. So if I represent a number n with 4 digits, the tens complement of n, which is a 4-digit decimal number, 4-digit decimal number, tens complement of n is 10 power 4 minus number n. If the number n is 1, 2, 3, 4, because there are 4 digits, it's a decimal system. And the tens complement of this is 10 power 4 is 10,000, right? 10 power 4 is 10,000, is it right? Subtract 1, 2, 3, 4 from this. How much is this? 6. 6, is it 6 again? Is it 7? 8. Is that right? 8766. So you just subtract the number from the number which is represented by the base to the power of the number of digits. Base or the radix to the power of the number of digits is the number from which you should subtract the given number, then you get the complement of that number in that system. There is also what you define R minus 1's complement, same R radix, R minus 1's complement is defined as R's complement minus 1. or if you want to put it the other way, it is of n. For n, r minus 1's complement is with n bits. For the number n with n digits, again, I could have probably used p digits or something, but choice is n, but doesn't matter. N is the small n is the number of digits, capital N is the number. I don't think there is any confusion in that. R minus 1's complement is here in this case you can write it as r power n. Since I have to subtract 1 from it, r minus n minus 1. From this I subtract n. So I will apply the same for the same number n, which is 1, 2, 3, 4. R is equal to 10. In this case R is equal to 10. And n is equal to 4 again. Small n is 4. I will use same n is equal to 4, R is equal to 10, capital N is 1, 2, 3, 4. But instead of r's complement or 10's complement, I will now define r minus 1's complement, which is 9's complement. R minus 1's complement is 9. So 9's complement is this is r power n, which is 10 power 4 is 10,000, but I have to subtract 1 from it. So it is 9,999. So it is 9,999 minus 1, 2, 3, 4, which is now 5, 6, 7, 8. You look at this number 8766, it is 8765. There is a one difference, which is that r minus n minus 1. Since I subtracted from r power n minus 1, for r minus 1's complement I subtracted the given number n from r power n minus 1. For r's complement I subtracted the given number from r power n. So that extra 1 from in my total from which I subtracted this number, that one is showing up here as one less than the r's complement. So for 9's complement of a given number, why is it convenient? Because 9's complement is nothing but the complement of each digit. Here I have to make a subtraction of 10 minus 4, so it is borrow is involved. 10 minus 4 is 6, so since it is 10 I had to borrow 1 from here. So when I borrowed 1 from here, this became 9 minus 3 is 6, and since this had to be borrowed, so this borrow travelled through. Here there is no such borrow condition here. Each digit, because maximum digit I can have here is a 9. The maximum value of this, any of these digits is 9, and this is 9999. I am going to subtract any number. Each of the digits cannot be more than 9. So all I have to do is a simple subtraction, digit by digit. So 9 r minus 1's complement or 9's complement in this case is easier to perform than 10's complement, which is some subtraction involves in borrow. So if you want to calculate 10's complement, I can always find 9's complement and add 1 to it. So 10's complement is of any number is 9's complement of that number plus 1. Why do we say all this? We will see in a minute. Before we go to the reason for doing this, besides subtraction can be done using complement system, there must be some obvious advantage. We talked about hardware. We talked about arithmetic units which need to do add, subtract, multiply, divide and everything, and I want to reduce the hardware or use a common hardware for doing more than one function. In that context, I have talked about complement numbers, which means subtraction using complement numbers can be done using the same hardware that we use for addition. That is why I am bringing this concept. I will tell you how. Before that, we have to switch to binary because we will be doing binary arithmetic in our digital course, logic design or computer design course. So this was to explain to you, because since you are familiar with decimal numbers, I introduced this concept of complementing of numbers using decimal concept, but in reality we are interested in binary numbers. So binary numbers, you have only r is equal to 2, that means I have 2's complement and 1's complement. So r's complement, r minus 1's complement, corresponds to 2's complement, 2 minus 1, which is 1's complement. So again, r power n, number of bits, minus the given number n, in the case of 2's complement, r power n minus 1 minus the given number n is 1's complement. So let us take a simple example without going through all these detailed definitions which I have already done in this case. In the case of decimal numbers, we will take an example of n is equal to 8 or even 4, make it simple, 4, that means a 4-bit number. In decimal you call it digits, in binary you call it bits. I mean, number n can be anything. It has to be a binary number, so I have to give it in binary. In decimal I took it as 1, 2, 3, 4. In binary I need to write it as a binary number. Let us say it is 0101, which is 5 really, decimal. 0101 is decimal 5, correct? So let me find 2's complement and 1's complement for this number. So n is equal to 4, capital N is 0101. So 2's complement is, or I will do it the other way now to make it easy for you. Let me first find 1's complement. What did I say for r minus 1's complement? I write the largest number possible with the given number of digits. In the case of r's complement, of course, I need to write plus 1, so that the base. All this I won't call it confusion. This difference between r and r minus 1 comes because we talked with 0. 0 has to be counted. If you don't have 0, then there is nothing like r's complement, r minus 1's complement. But 0 is very important. We have to represent 0. And you know that is India's contribution to mathematics. Not 0, I think. 0 was contributed. I think it looks like now it is 0 is the contribution. Anyway, 0 is important. So nowadays, 1's complement, what is the maximum binary number, the largest binary number I can represent using 4 bits? 1111. I subtract capital N, which is 0101 from this, I get 1's complement, add 1 to it, I get 2's complement. Is that right? So 1's complement is 1111 minus 0101. Now again my binary arithmetic does not require borrow, because either a 1, always 1 on the top, either a 1 or a 0 in the bottom, so either it is 0 or a 1 result. So I don't have to worry about borrow from the next location, next bit position. Sort of makes sense because maximum with 4 bits, 1111 is 15, and this is 5, this is 10. Total should make 15. That's all. There's no big magic here. We are giving a number. We are finding its complement. Complement. You know what a complement is? Complementary angles and all that you have studied in trigonometry. So if something is given, what is not given is a complement from the total. You subtract what is given from the total, you get complement, right? The total is 1111, given is 5, So the complement is 10. And 2's complement is 1010. So when you add 2's complement and the given number, it should give rise to 1 more than 1111. 1 more than 1111 is 16. 1111 is 15. 1 more than 1111 is 16. This is 11. Given number is 5. So total is 16. That also tallies. So this addition of 1 gives me 2's complement. That is because now if you want to do it the rigorous way, it is r power n, in this case r is equal to 4, r is equal to 2, 2 power 4, 2 power 4 is 16. 16 in binary is not 1111, 4 bits, alright, but since 0 is counted, 16 becomes the first bit of the next position, 5th position. So I need 5 bits to do that, which is 1 0 0 0 0, subtract 0 1 0 1. I do the same one. So now you have to use the borrow arithmetic, and then this is 1. Same thing here, because it's been borrowed here. So this one is, so this is 1 0 1 1. 16 minus 5 is 11. So I can always find out the 2's complement of given. We need 2's complement and 1's complement in our subtraction. We will see that when subtract. We want to do subtraction not by designing a subtractor. Subtractor can be designed as you design a adder, starting from the requirement. Problem statement, truth table, Boolean algebra, corner map, reduce, gate structure. Fine. Nothing wrong in doing the subtraction like that. Don't think that it should not be done that way. Because we want to have a common hardware for adder and subtractor, functionally we want to make it as compact as possible, because you are not, it is very very unlikely that you are going to add and subtract at the same time. Very very unlikely that in a computer, in an arithmetic unit, in a calculator, you are going to do subtraction and addition simultaneously. You will do one after the other. So I can use the same hardware piece. So when you do subtraction by complement method, I can show that and same adder can be used to do subtraction. That is the object of the whole exercise now. So a given number, you are asked to find the 2's complement, 1's complement, no problem. You complement the given number bit by bit. Complement the number, given number by bit, you get 1's complement. Add 1 to it, you get 2's complement. Okay? Now, where does it fit in the case of subtraction? Now, subtraction is same as adding the complement of that number. Okay, 2's complement number, if you add to a given number, suppose I want to subtract b from a minus b, I want to find out. Instead of designing a logic for subtraction, I can use an adder logic and add instead of b the complement of b. A plus complement of b is same as a minus b. That's all there is to it. That is why we need to know complement, so that we can use the same adder which you have designed, whether it's a straight adder or a carry lookup adder, whatever adder. The same hardware or the functional unit called adder can be used for subtraction. So let us do this example. Subtraction using 2's complement. So let us again take a simple 4-bit example. Now I want to subtract a minus b. Let us say a is 1100, b is a is 12 and b is 5. Isn't that? 12 minus 5 is 7, I should get answer, which is 0 1 1 1. So what you do is, I write a as it is, I find 2's complement of b. So 1's complement of b first write. 1's complement of b is 1 0 1 0. That means complement bit by bit. Each bit you complement. That is 1's complement. Add 1 to it, you get 2's complement. So I am now going to add 2's complement of 0 and 1, add what is this? 1 plus 1, 0 with a 1 carry 1. This extra carry which is not required in this case, because this is not a, we are talking of 4-bit number. Here you have to be careful, there is a little sort of a caution here. I am dealing with 4-bit numbers, A and B. A is 4 bits, B is 4 bits, so I am expecting a 4-bit result. It is not A plus B, the result can be 5 bits. A is 4 bits, B is 4 bits, I am subtracting A minus B, the result has to be 4 bits. So all I have to do is to discard this. Discard that carry, ignore it. So because I know that the result is going to be 4 bits or less, I discard the last bit. Now this number is, how much is this? So this is discard, carry. What is this number? 0 1 1 1 is 7. So 12 minus 5 is 7. I can also do it 1's complement way, but then I will get one less number and I add 1 to it finally. Suppose I do 1's complement addition, A is 1's complement of A, B is what? B is 0 1 0 1, 1's complement is 1 0 1 0. Is that right? B is 0 1 0 1, 1's complement of B is 1 0 1 0. Add now I can't discard this carry because I know that one carry has to be, because this carry can be discarded, I have to add 1 to it. I can discard this carry and add 1 to it. Add 1. Or you can say, sort of, it's not logical. This one is brought here and added, they say. It's called end around carry. You will see in the book, it's called EAC. You bring the carry around and add it here. It doesn't make sense. You have to add 1 to 2's complement number. It is not a magic or something we are showing. So it is a logic. So you have to add 1 to this because it's 1's complement and you want 2's complement. 2's complement gives the subtraction number. The subtraction of two numbers, subtraction of B from A, the result is the 2's complement addition of A and B. In other words, A minus B is same as A plus 2's complement of B, not 1's complement. Since we need to have 2's complement and we have done only 1's complement, I have to add anyway 1. Somewhere 1 has to be inserted. That 1 is inserted here, but it's okay. It happens that we are going to discard 1. You discard 1 and then add 1, so it's as if you are bringing it back and adding it. I think it is more for people to remember it. There's some sort of a tip for remembering that 1 has to be brought. So they say bring this and add. That's not. But then you will find it is a very serious thing. In the book you will say end around carry. You bring it back, they will put an arrow like this and show it like this. If you want to do it, fine, no problem, as long as you understand what is happening. Now we are talking of a positive number subtracted from a positive number, the result is a positive number. supposing I have a number from which I am subtracting is larger than the given number, the result will be negative. We will also look at that possibility. What will happen if the subtracted number is negative? I mean subtracted number, I mean the difference is negative, which happens when n is, we will put the other way, 5 minus 12. Can I now say A is equal to 5, B is 12, the result has to be minus 7, is that right? So I will do this. A is equal to 0, 1, 0, 1. 2's complement of B. By now you know how to do that. This is 0, 0, 1, 1. Add 0, 0, 1, 1. To that you have to add 1. So what will be 2's complement of B? 1, 0, 1, 0, 0. Right? That is because 1's complement is 0, 0, 1, 1. 2's complement is add 1, this becomes 0, 0, 1. Add A minus B is same as adding A and 2's complement of B, which is 1, 0, 0, 1. Is that right? Is that right? You mean the answer is right? My addition is right. The answer is not right. Now, and there is no carry here, you see, significantly. There is a carry here, is a 0 in the last digit. So, when there is a 0 in the last digit and a carry, it represents the positive result. The difference is positive. Whenever the difference is positive, you will have a 0 in the last bit position, which is required bit position, and this 1 which is going to be discarded. There is a 1 in the discarded position to be discarded, 0 in the last position of interest. Here it is exactly the opposite. I have a 1 here in the last position of interest and 0 in the discarded position, to be discarded. So this gives a signal, this is a negative number. If the last position of interest is 0 and 1 pairs of carry which has to be discarded, then it's a positive result. Answer is right. If on the other hand you get a 0 here and a 1 here, you know it's a negative number. So that means I have to get a 2's complement of that before I can. The correct answer is not this. The number is the 2's complement of the difference. So if I take the 2's complement of this number, so I will call this 2's complement. This is not A minus B really. This is A minus B, let us say star. And if I take the 2's complement of this, this is going to be 1's complement plus 1, right? 1's complement is 0, 1, 1, 0. Add 1 to it, I get 2's complement, which is, what is this number? 0, 1, 1, 1, 7. But you should not take it as 7 because of this. This is minus 7. So when the number is negative, you take the 2's complement and give the negative sign to it. The number is positive, you take the number as it is. How do you know it's a positive number or negative number? The discarded bit is 1 in the case of positive numbers, and the last bit of interest is a 0. The last bit of interest is 0, is a positive number. This is called MSB, most significant bit as far as we are concerned. This is the most significant bit, this is the least significant bit. I think we already mentioned this once. When you have several bits, the lowest significant bit, next higher, the maximum significance is this bit. So this is the MSB. and this is LSB. So if MSB is 0, this is a positive number. Forget about discarding, because anyway we are going to discard that 1 and 0. Here this 0 is discarded, there 1 is discarded. So let us not worry about that. Is an extra signal for you, but don't worry about that. I have this most significant bit as 0, it's a positive number. Here I have the most significant bit as 1, which is a negative number. Once the result is negative, the 2's complement addition of B to A does not give you A minus B if the difference happens to be a negative number, indicated by the fact that MSB is 1. If the MSB is 1, the difference A minus B which is computed by adding B's 2's complement of B to A is not the correct number. It is the 2's complement of that difference which is the correct number, which is this 2's complement. But you don't have to worry about it, because this will be again, this is a negative number. Instead of saying minus, how do you say minus 7 in a computer? You add 7, you can put 7, binary 7, you can put binary any number. How do you put minus sign? I said all symbols have to be represented by binary codes, whether it's in alphabets, special symbols, comma, punctuation, email, letters, database, marks. It's all binary numbers, binary digits, bits. So negative has to be somewhere. So that is our way of telling the computer is a negative number is also the same way. The computer's way of telling us it's a negative number is also the same way. So in any number of bits, you define the number of bits in a number. The most significant bit, if it is 1, it is a negative number. The most significant bit is a 0, it is a positive number. So even though it's for our consumption, for our understanding, to make sure that I have done this arithmetic right, to make sure that my arithmetic is right, I want to do this 2's complement and check whether it's really 7. I knew it is 7, I knew it is negative, but I am not sure it is 7. How do I check it is 7? By taking 2's complement and finding out it is indeed 7. But this is 0, but I know the number is negative, so I cannot have a 0 here when the number is negative. The answer is minus 7. When the answer is minus 7, I can't have a 0 here. I have 1 here. So negative numbers are represented in computers by 2's complement, whose MSB is 1. So if you want to give a negative number input to the computer, you don't give a number and punch in this negative sign in the calculator. Of course you type that, but minus does not, that minus or sign of the number, you have this in the calculator, plus minus sign, if you punch that key, a minus does not go and get stored. The minus translated immediately, you have to convert whatever number you had written earlier, had to be converted to 2's complement and stored with a negative 1, with the 1 MSB. So MSB 1 is the significant, MSB 1 is indicative of the fact that the number is represented as a negative number is represented. Similarly, the computer, when it finds out the result, gives you a negative number. In the case of negative numbers, it gives a 1 as MSB. You know it is a negative number. You deal with it the way you want. It is the final step and you want to give the answer to the examination. Then you won't write it like this, you will say it is a minus 7 in your answer paper. But if this is going to be fed into the next stage of computation, because after all you do computation, it's a long equation or whatever arithmetic problem solving, this is an intermediate result which will feed into the next stage. At that time again you have to feed minus 7 to the computer. The computer, we don't have to worry about translating into minus 7 and making it plus 7 again and then minus 7, all that step. So this is minus 7. This extra step was just to tell you it is not wrong arithmetic we did. I showed you that right arithmetic is all right arithmetic only. So the answer is this, in the case of 5 minus 12, and this in the case of 12 minus 5. In the case of 12 minus 5, the answer is plus 7, so it is 0, 1, 1, 1. So 0, 1, 1, 1 is plus 5, or 0, 1, 1 is plus 7. So now the sum up, it is 12 minus 5 is plus 7, 0, 1, 1, 1. 5 minus 12 is minus 7. And if you don't believe me, All I am asking you to do is to take the 2's complement and see it for yourself. It is 7. That's all I am saying. Any questions here? The complementing of numbers makes subtraction and adding operation. That is where the crux of the whole matter is today. I introduced number systems, in complement number system, to tell you. Of course, I could always told you this is the way to do arithmetic, but I thought I wanted to tell you why they do it. Why they do it is 2's complement numbers. If you can add and then get a subtraction performed. Subtraction is reduced and addition operation, not reduce. If you don't want to call it reduce, converted. Why do you have to do that? I can have a single hardware called adder, one hardware unit, and since I am not going to use the same hardware both for adding and subtracting at the same time, when I want to add, I add, when I want to subtract, I subtract. All I have to feed is the numbers in 2's complement form. If I feed the numbers in the regular form, it gets added. In 2's complement form, if you put it, it gets subtracted. So the question now is, how do you convert a given number to 2's complement number? That is extra logic, is it not? As I said, nothing is free. There is no such thing as free lunch, as they say. You know? Somebody invites you for lunch, you know that there is something else coming for a favor. So that means you need to do something to get these 2's complement numbers. And but it's easy, because all you do is inversion and add 1. How do you get an inverter of a number? Just pass it through an inverter. So quickest way to invert is to put an inverter, which all of us know. So first I will tell you how to get 1's complement, then we will see how to do 2's complement of a given number. So now I have now reduced the subtraction to if you all agree on this. Is there anyone who doesn't agree on this? You better. Okay. Now, next step is how am I going to convert a given number to 2's complement before I can add it. So first let us do 1's complement. That is why I told you the hardware wise it is easier to do that 1's complement and plus 1. Even though in principle you want to do this borrowing from the previous, all those things I want to avoid. A simple complementing will give you 1's complement. All I have to do is to add an extra 1 somewhere. I can do it at the beginning or I can do it at the end. Is it not? So 1's complement is an inverter. So if it is A bar, no problem, any bit. But the problem is, a given bit A can be converted into 1's complement with an inverter, but I don't know when to convert, when not to convert. When it is adding operation, I have the same hardware unit called adder, in which I give A and B without converting, it adds up. When I give A and convert B as 2's complement and feed it, it subtracts. So I need to know when to give the number directly as a correct number, when to give this number as a 2's complement number. Whenever I need subtraction, I need to give it as a 2's complement number. Whenever I need addition, I need to give it directly. So I need to have a control of this addition, converter. I need to have a control of this inversion operation whenever I need. It's a very simple technique for that. Let us do an exclusive OR gate. Suppose I have an exclusive OR gate. This is the number I want to invert, AI. Not always, but whenever I want. When do I want? When S is equal to 1. S is a subtraction. Suppose I give my S here. The second input is A. If this is 1 and this is 1, what is the output of exclusive OR gate? 1, 1 is the exclusive OR input, output 0. When this is 0 and this is AI, this also becomes AI. So when S is 0, that is for add. When I give S is equal to 0, it is addition operation. This is AI bar. This is AI bar if S is equal to 1, AI. Do you agree with me? If S is 0, this is 0, this is 0, this is 1, this is 1. S is 1, if this is 0, this is 1, this is 1, this is 0. So whenever I want to invert, I give S is equal to 1. Whenever I do not want to invert, I put S is equal to 0. Now not only I can invert and get 1's complement, I can do it at will. Do it when I need it. So my simple 2's complement circuitry or 1's complement circuitry is a bank of exclusive OR gates to which I feed the inputs. So this is my 2's complement, 1's complement circuit. I will call it 1's complementer because we want to give big names to small things, right? My 1's complementer hardware I give a series of exclusive OR gates. Let us say 4 bits. Let us be happy with 4 bits today. A0, A1, A2, A3 or B. Because we said B, A is B. Just, it can be anything. I just, for sake of continuity of the lecture, I am giving B's. Because A minus B or A plus B, you know. So B I am converting. Can be A, can be P, can be Q. Doesn't matter. Now I am going to connect all the other inputs together and give this as S. Whenever I want subtraction, I make this S is equal to 1. I get B bar, B0 bar, B1 bar, B2 bar, B3 bar. Whenever S is 0, that means when I add, S is equal to 0 for add, 1 for subtract. So if it is adding, it is A0, B0, A0, A1, A2, A3 will come out. Subtraction, A0 bar, A1 bar, A2 bar, A3 bar. So A3 bar will come out. So it's 1's complementary circuitry. Of course I have to add 1 to it. We will see how to do that. So all I have to do it now, I have an adder which we did elaborately in the last couple of lectures, and I now have a 1's complementer, which is simple logic. I also proved to you that 1's complementer or 2's complementer can be used in conjunction with an adder to get a subtraction done. All I have to do is to glue it together, put it together to get a subtractor. We will see that in the next lecture, how to get the subtraction. Now there is nothing, you can do it yourself. I have an adder, I have a complementer. What else do you need? Tell me, where do you give that extra 1? Carry in is usually 0. Carry in is usually 0 in adder, right? First stage carry in is always 0. You make it 1. Not always 1, whenever you want subtraction. So you make that same as S. So I have a full adder. A directly feed, B feed it through this complementary circuitry and connect C to the same S which is going to control the complementary circuitry, and then output I get. Fair enough. Very simple. All I have to do is to do the drawing part of it. You can do it yourself. It's in the book. Just have to draw this complementer, direct input, complementary input, S being controlling the complementing as well as the carry input. You get the output result as negative A minus B. Are there any questions? Okay.